Welcome back to Cooperative Communication Systems. I'm Jang Nguyen, and today we work on exercises for P2P video streaming. Let's start with exercise 1, the basic. We have two questions. The first one, what are the main advantages of P2P video streaming? Alright, there are several advantages, but the main ones are: first of all, it is cost effective. The reason is, peer comes with their own resources, mainly the upload bandwidth. So the more peers come to our system to share the video, the more overall upload bandwidth the whole system has. The second advantage is that such a system is relatively scalable without the need to upgrade the underlying switches, routers, because the whole P2P video streaming application is running at the application layer, where we can update the software as we want, and therefore we are not strongly dependent on the underlying infrastructure. And the third main advantage is that it is relatively easy to deploy. Reason the same as above. It is running on the software, and as long as all the peers are running on the same version of the software, it should be easy to deploy. Now, coming to the main challenges of P2P video streaming, I would like to highlight three main challenges. The first one is that peers are inherently unreliable. What do I mean by that? Peers can come to join the system and then contribute to the overall resources of the system. However, they can also leave the system at will at any time that they don't want to participate anymore. And when the overall resources of the system, and thus the overall performance of the system, is dependent on the will of the peers, it is very difficult to assure a certain quality of service. Furthermore, all the hardware and software stack of the peers are normally for personal use. They are not dedicated to support others under high load, working for a long time. And therefore, when they have to use for a long time, they have to operate under the high pressure, they might fail. The second challenge of P2P video streaming is that it is rather difficult to build and maintain optimal topology, the overlay topology among the peers. So if we consider a push-based system where we need to build like a tree or multiple trees among the peers, then those trees has to be loop-free. What is the consequence of a loop of a topology with the loops? In that case, the video packets will be forwarded again and again and again among the peers without any new information, and therefore the live stream updated video packets cannot be delivered to the peers who need them. The third challenge for P2P video streaming is that it is also difficult to maintain scalability and at the same time the high quality of experience when people watching live video streams. The reason is, the larger the network it is, the longer the path from the source that stream the videos and on other peers. And the longer path meaning higher latency. And since peers at the end of the path are dependent on several peers in the between, and therefore they are more subjective to errors. Now let's move on to the second exercise about the types of topologies. Let's start with the first two questions. Number 1. Characteristics of the tree topology in a push-based system. So in a push-based system, if we consider a minimum topology of 2 peers, then they have to maintain an explicit relationship. One node has to be a parent node and the other one has to be a child node. And as soon as the parent node receives the video packet, the parent node will forward the video packet immediately to the child node. And a larger system of multiple peers will consist of multiple parent node child node pairs. And for each peer in the system, there is only one single source to peer path. And for that reason, the tree topology is more fragile than other topology types. Why is that? Because there's only one single source to peer path. And in order for the peer at the leaves to receive the video packet, the whole path from the source to multiple intermediate nodes has to be maintained. If for a certain reason, like the node leaves or due to failure, the path from the source to the peer is broken, and therefore the peer at the end of the path cannot receive the video packet anymore. Now let's move on to the mesh topology of a pool-based system. What are their characteristics? So in contrast to the tree topologies with explicit relationship between any two peers, all the peers in a mesh topology maintain the partnership relations. There's no child node or parent node anymore. They're own partners, and therefore video packets can go from one direction or the other. And for that reason, there are multiple source to peer paths for any particular peers. As a consequence of that, the mesh topology are better in connectivity. If for certain reason a path is broken because the peer fails or leaves the system, then the video packet can travel another path. Now let's come to the third and the fourth questions in this exercise. So the discussion, the prior discussion already answered the third question about the main differences between the mesh and the tree topologies of P2P video streaming. Now let's move on to the fourth question about the characteristics of the overlay topology in a hybrid system. So if we recall the lectures a few weeks ago, a hybrid system consists of two types of overlay topology. It consists of both the tree topology and the mesh topology. And the tree topology is used to construct the overlay in the backbone, while the mesh topology construct the overlay in the outskirts. So in this way, the hybrid system can combine the advantages of both types of overlay topologies. More connectivity for the outskirt, which is using the mesh topology, and the tree topology for the backbone to provide low latency. Let's come to the third exercise. In the previous exercise, we talked about the overlay topology. Now, in the third exercise, we are asked about the transmission paradigms given the topologies, tree, mesh, or hybrid. What are the way that video packets are disseminated over or on top of those topologies? First question, characteristic of push-based. So for push-based system, we use the tree topology, and therefore the latency is very low. If we recall the push-based systems, video packets is forwarded immediately or as soon as it's received at a parent node. It will be forwarded immediately to the child nodes or several child nodes. And this type of dissemination provides low latency. It also provides low overhead because there is no such thing like request and response, no signaling is needed. Receive, forward immediately. In contrast to that, the characteristic of pull-based streaming is high latency. The reason is every peer in the system has to ask for the video packets that it needs, and therefore it takes some time from looking at itself to find out which video packet is needed from which peer, send the request to the peer, and then waiting for the response, and therefore it is higher in the latency. The request response model in video packets dissemination also higher in overhead. If we count for the on the packets or on the messages for the request and response, and also exchanging the video buffer mapped from each peer so that they know or other partner knows which packet it has so that it can request. So the previous discussion already answered the third question. Now come to the fourth question about dissemination in hybrid system. So again, the hybrid system combines advantages of both pull-based and push-based. In the backbone, because of the tree topology and employing the push-based system, and therefore the overall latency can benefit from a low latency and low overhead. And at the same time, at the outskirts, when peers maintain the mesh topology with the pull-based type of video dissemination, it has the high. So comparing to so if we talk about latency, then the lowest is the pull-based, then the hybrid, and then the other way around. So if we talk about latency, then the lowest in the latency is the push-based system, and then the hybrid, then the pull-based. If we talk about the overhead, then we have a similar order. So the push-based system has the lowest overhead, then we have the hybrid one, and the last one in the order is a pull-based system. Now let's come to a question about multiple tree push-based system. So in a multiple tree push-based system, the system maintains multiple trees or multiple overlays to disseminate the video packets. And in order to do that, it has to disseminate the video packet in a different way. And splitting the whole video stream into stripes is what is proven a very practical way and efficient way to obtain the goal. And how can we do that? If given the stream consisting of video packets with the sequence numbers from 0 to 9, how can we do that? So the solution is that we form three stripes, 1, 2, 3. So 1, 2, 3, and the stripe number 1 consists of video packets with the sequence number 0, 3, 6, 9, 12, 15, and so on. Stripe number 2 consists of video packets with the sequence numbers 1, 4, 7, 10, and so on. And the last part, the last stripe, consists of all the rest of the video packets. Exercise number 5 continues with multiple tree push-based systems. The first question is about the inner node disjointness. What does that mean? And it means that all the inner nodes in one tree are the leaf node in all other trees. Now let's have a look at one example of the tree. Here we have 10 nodes from 1, 2, 3 until 8, 9, 10. And among them we have inner nodes 1, 2, 3, 5, and 6. Inner node means they are child node for others, and at the same time they are parent node to others. For example, node number 1, they are the child node with regard to the source, and they are parent node for number 4. Inner nodes are important because the rest, all the leaf node, are dependent on the inner node to receive video packets. And if any of the leaf nodes fails or leave the system, then the nodes dependent on that inner node will not receive the video packet anymore. And the inner node disjointness will ensure that no inner nodes are very important, critically important in all the trees, and therefore the system are not totally dependent on any of the nodes. This is due to the inherent unreliability of the peers in a peer-to-peer video streaming system. Now let's move to the second question in this exercise. Here is the overlay of a push-based system with 2 stripes. The requirement is that we build a second topology, second tree, satisfying the inner node disjoint requirement. So first of all, there are many solutions for this. Here I will present one solution. Now here, if we go back to the inner node disjointness requirement, then we only need to make sure that all the inner nodes in stripe number 1 will be the leaf node in stripe number 2. So all the nodes 1, 2, 3, 5, and 6 have to be the leaf node. The rest of the nodes can either be the leaf node, as in stripe number 1, or can also be the inner nodes, like 4, 7, 8, 9, and 10, their own inner nodes. Again, one remark is that there are many solutions for this. Since there is no constraints about the bandwidth in the system, then we can build many different topologies. For example, node number 4, it can upload to 2 other nodes at the same time. If the upload bandwidth of node number 4 is even higher, it can upload to maybe 3, 5, 10 other nodes at the same time, and then in that case node number 4 can have more children. Exercise number 6 is about pool-based systems, and specifically is about the scheduling algorithm. And it's about the rarest first scheduling algorithm. Here we have the information about the buffer maps of 3 peers, A, B, and C. Here are the sequence numbers of the video packets. So packets number 3, number 4, 5, and so on until number 9, number 10. So the number 1 indicates that video packet is available at peer A or at any particular peer. Here we have video package number 3. It is available at peer A, B, C. So all of them have packet number 3. For packet number 4 or video packet number 4, it is available at peer A, peer B, but unavailable at peer C. The question is, if we consider peer A and it has to run the rarest first scheduling algorithm, how peer A will request video packets from B and C given their video buffer maps like that. So let's start. Now from the video buffer map, we know which video packets are already available at peer A, and therefore peer A doesn't have to request those video packets anymore. And also looking at the buffer map with the 0 bit, we know that peer A still have to request video packet number 6, number 7, number 8, number 10, because the respective bit for those video packets are 0. So having those information, we can construct a table with the video packets 6, 7, 8, and 10. And by looking up at the buffer maps of peer B and peer C, we know that video packets number 6 is available at B and C. Number 7 available at B but not C. Video packet number 8 is available at both B and C, and the last video packet number 10 is not available at B but available at C. And here are the total number of copies of a certain video packet. So video packet number 6 has 2 copies at B and C. Similarly for video packet number 8. On the other hand, video packets number 7 and number 10 are only available at one of the peers, and therefore they are the rarest video packet. Now what can we do with this? We have to start with the rarest video packets first, right? So rarest first, number 7 and number 10, because they are only available at one of the peers, we have to request them at that peer anyway, no other choice, and we have to request them immediately. So this is the first step to request. Now after requesting those video packets, I mean number 7 and number 10, we will look at other video packets 6 and 8. They are available at at least 2 other peers. So in this case B and C. And then the question is which one we will request from which peer. So because 6 is supposed to arrive before 8. Why? We are talking about a live video stream, and each video packet has its own deadline. If the video packet misses its own deadline, then the video packet is useless. Therefore, if we request video package number 6 first, we have a higher chance. We cannot be sure, but we only have a higher chance that 6 will be if number 6 is request earlier, then it has a higher chance to arrive earlier than number 8. And here we can either request number 6 and number 8 both at B or at C, or we have a chance to request number 6 at B and then number 8 at C. So more or less we spread the load, balance the load of uploading between different peers so that they are not overloaded, and therefore we have a higher chance, or peer A has a higher chance of receiving all the video packets in the right order before their own deadline. Let's move on to the last exercise number 7, about hybrid systems. First question about the reason why a backbone of a hybrid system consists of stable peers. So this is based on the observation from a measurement study of a running pool-based system. And the author of the studies found out that 20%, so around 20% of the connection between any particular peers in the system deliver a large number, in this case almost 80% of all the video chunks. So it means that those connections, so there are small number of connections that are very important and staying in the system for a long time, and the peers forming those small number of connections are called stable peers. And how precisely stable peers are defined? They particular peer so the if peers stay if the time that any particular peer spend in the system exceed a particular threshold, then we call those peers stable. And the reason that long peers staying long spend long time in the system are more stable than others, because also from the observation that the longer the peers stay in the system, the more likely that they will stay even longer in the future. Now, the last question. What are the two main optimization operation in MG-born one exemplary hybrid system? So we have two operations. The first one is high degree preemption. So it means that a peer with more children will preempt its own parent, so take the position of its own parent who has less children. Why is that? Because the peers with more children, it is more if the peer with more children has if the peer has with more children stay further away from the source, from the video source, it means that a large number of the children will also receive higher latency, and therefore the higher the peer with more children can be close to the source, the lower latency the overall system can have. The second operation is low latency jump. It means a peer will select a new parent with less latency. So in this case, peers will simply collect information about different other peers, about how close or how further away a particular peer is located from the source. And as soon as it discovers another peer whose latency is lower than its own parent, and that peer still has available resources, upload bandwidth to send video packets to another one, then the peer will select the new parent. Alright, so now we already went through all the 7 exercises. So if you have any question about that, feel free to send me a mail. Good success for your exam.